This video introduces the concept of input offset voltage, sometimes abbreviated as V-offset, explores how it affects the equations for the non-inverting and inverting amplifier circuits, presents an effective circuit for precisely measuring an op-amp's input offset voltage, and concludes with a lab demo that uses that circuit to measure an LM324's input offset voltage. So here we have our op-amp circuit with the tenets of the ideal op-amp listed below. The input offset voltage of a real op-amp alters this first equation that governs Vout. In order to explain what input offset voltage is, I'm going to take a short detour into the internals of an op-amp, but we won't go too in-depth in this video. The input stage of op-amps looks similar to this. In reality, the input stages of modern op-amps tend to be much more complicated than this, but this is a good enough representation of an op-amp input stage for explaining input offset voltage. We see here that the input stage is a differential pair. I've depicted it with NPN bipolar junction transistors, but it could be PNPs, MOSFETs, or JFETs depending upon the type of op-amp. The two inputs of the op-amp drive the two transistors, and the differential output, denoted as Vout diff, is transmitted to the later stages, though it's worth noting that the differential output is generally converted to single-ended shortly after leaving the input stage. Once it leaves the input stage, it undergoes additional amplification, frequency compensation, and conditioning before being output by the op-amp's output stage. In this circuit, both transistors are designed to be as close to identical as possible, and the two collector resistors on the top are designed to be as close to identical as possible. I've neglected any biasing circuitry as it would only add confusion, and the standard way of biasing discrete transistors using resistive dividers is much different from the way it is done in integrated circuits. So just assume that the input voltages VOP- and VOP+ are at least several volts higher than VEE and several volts lower than VCC, and that the transistors remain in the forward active region for all applicable input voltages. Assuming both transistors are identical, and both collector resistors are identical, you can imagine that identical voltages at VOP- and VOP+ will produce identical collector currents through the two upper resistors, which will produce a Vout diff of 0 volts. Increasing the voltage of both sides slightly, by maybe 10 millivolts, will produce a decrease in the common mode voltage of the two collectors, but no change in Vout diff. It will still be 0. The transistor circuits are matched by having them close together during fabrication, so that the doping concentrations and doping regions of the parts of the two transistors are very similar. There are also many proprietary processes and tricks used by semiconductor manufacturers to improve the matching between them. However, there still is a mismatch between these two transistors, as well as the other elements in the two sides of the input stage, such as the resistors at the top. They cannot ever be perfectly matched. And so when the same voltage is applied to VOP- and VOP+ as before, there will be a non-zero differential output voltage. In order to make the output voltage 0, a small difference between VOP- and VOP+ must be introduced. This small difference, or offset from each other, is referred to as the input offset voltage, and it represents the amount of voltage the inputs need to be offset from one another in order for the output of the op-amp to equal 0 volts. The input offset voltage can be positive or negative, and it generally changes to some degree based on temperature, time, common mode voltage, as well as other parameters. This effect is captured by adjusting our ideal op-amp transfer function with the addition of the input offset voltage, denoted as VOS. Note that all other ideal op-amp equations are still kept, including the infinite gain. Now let's explore the differences between the ideal op-amp and the op-amp with V-offset incorporated. Looking at the ideal equation, and the gain going to infinity, we recall that since this gain is a value going to infinity multiplied by the differential voltage in parentheses, we know that the differential voltage must go to 0 in order for Vout to be a finite value. If it did not, then Vout would have to be infinity. So again, the differential voltage is 0, meaning that VOP+ is equal to VOP-. Now looking at the op-amp with V-offset, we have the new equation with VOS, with gain still going to infinity. Thus, the expression in parentheses with VOS must go to 0 for finite Vout. And thus VOP- is equal to VOP+ plus VOS. I've written it this way because typically VOP+ is directly controlled and VOP minus is connected to Vout through feedback. And so we can usually calculate VOP plus first, and VOP minus requires solving some equations incorporating the feedback network. Now let's see how this affects the non-inverting amplifier circuit. So recall the non-inverting amplifier circuit here, with VOP plus connected to Vin, the input voltage applied to the circuit, and VOP minus equal to Vin plus VOS from the new op-amp equation we just derived, shown in green. Using similar methods to derive the output voltage, we apply the resistor divider equation as though Vout is the desired variable. We then invert the equation to get an expression for Vout in terms of VOP minus. Next, we substitute in the expression for VOP minus and separate out the Vin term and the VOS term. I separate it out this way even though they have the same coefficient to emphasize the difference between the ideal case and the non-ideal case. In the ideal case, Vout is just Vin multiplied by the non-inverting gain, R1 plus R2 over R2. With V offset, we add this additional term, the offset voltage multiplied by the non-inverting gain. This makes sense intuitively if we think about the circuit from a superposition standpoint. If we zero out V offset and use the ideal op-amp again with just Vin, we get the ideal solution. If we then zero out Vin and only use V offset effectively acts like a Vin with a value of VOS, thus resulting in Vin times AV non-inverting. Adding these results both together gets the equation we've just derived. This result is very important for designers because V offset can be a significant error term in a sensitive signal chain and must be compensated for. Additionally, if you have a lot of gain in your signal chain, your entire signal chain can rail with no signal if you're not careful to keep the offset of the first amplifier low enough. Now we examine the effect of input offset voltage on the inverting amplifier configuration. First off, we're setting VOP plus to 0 volts as we did before, and we note that VOP minus equals 0 volts plus VOS as defined by our new equation. This may look familiar because it is the same as the inverting amplifier with offset, which has the VOP plus input connected to a voltage VA. It generates the same voltage on VOP minus, except the voltage becomes VA instead of VOS. So we can simply use the inverting amplifier with offset equation we derived in episode 8, except substituting in VOS in place of VA. So we see that the offset is gained up by the same factor for the inverting amplifier as it was for the non-inverting amplifier. This is not surprising, because if we think about it from a superposition standpoint, the inverting and non-inverting amplifier circuits are identical when the input is zeroed out, and only the offset voltage is considered, and so the portion of the output that is influenced by the offset voltage is the same for both circuits. Now that we've looked at a couple case studies, next we'll show a circuit for making precise measurements of an op-amp's input offset voltage. Then we'll demonstrate that circuit by measuring the input offset voltage of an LM324 in the lab. So the simplest way to measure input offset voltage, you would think, would be to just use a unity gain buffer, ground the non-inverting input, and the output will be equal to the offset voltage. However, this is an extremely inaccurate way of doing so, as input offset voltages are almost always less than 50 millivolts, which is a difficult voltage to measure accurately at DC, and many op-amps have significantly lower input offset voltages, with some very low offset op-amps possessing input offset voltages lower than 250 nanovolts. As a result, it is far more prudent to construct a circuit that utilizes some of the op-amp's gain to gain up the signal so as to minimize the measurement errors. A useful circuit that does that is this one. Here we have two cascaded op-amp circuits. The first op-amp, OA1, is the device under test, or DUT. The DUT's input offset is the parameter we're measuring. The second op-amp, OA2, is in the integrator configuration with a resistor in series with the integrating capacitor. This indicates that at high frequencies, the subcircuit containing OA2 acts like a simple inverting amplifier. The way this overall circuit works is very similar to a simple non-inverting amplifier. The difference is that an integrator containing OA2 is in series with OA1 inside of its feedback loop. Let's ignore this for the moment, seeing that it only serves to increase the overall open loop gain of the system, and thus we can treat the combined two op-amp circuit like a single op-amp circuit in non-inverting configuration. We see that similar to the non-inverting amplifier, we have our op-amp in the green box and our feedback network encompassed in blue. Our input is connected to ground through resistor R1. This resistor helps cancel out input bias currents, which is something we'll discuss in detail in a later video. For now, we just set R1 to a value close to the parallel combination of Rin and RFB. The resulting output voltage is approximately equal to -1 times the DUT's input offset voltage multiplied by the non-inverting gain, which is RFB plus Rin over Rin. So we just measure the output voltage Vout2 with our DMM or other measurement device, divided by the non-inverting gain, then multiply that value by -1 to compute the DUT's input offset voltage. The -1 is required because the OA2 circuit introduces an inversion into the system. This is also the reason that the feedback network connects the output to the non-inverting input of OA1 rather than the inverting input. Now we focus on the integrator circuit containing OA2 inside of the feedback loop. The addition of this circuit inside the feedback loop of OA1 does three important things. First, it increases the open loop gain of the circuit. Recall that open loop gain is the gain of the op-amp without feedback. In the ideal case, it is infinite, but it is finite in the real case. This effectively creates an op-amp feedback system with a gain of OA1's open loop gain times OA2's open loop gain, at DC. This reduces the effect of finite gain to be truly negligible, even in the case of very small input offset voltages. At higher frequencies, the additional gain of the circuit causes stability problems, and so since only the DC gain is needed for the input offset voltage measurement, we configure the OP2 circuit as an integrator rather than an inverting amplifier with a large feedback resistor to eliminate the gain at higher frequencies. The resistor in series with the capacitor also helps with the stability by canceling out the integrator's pole prior to the gain crossover of the system so that the phase margin remains high. We'll discuss feedback stability considerations in a later video. Secondly, it keeps the output of OA1 very close to ground. This is important because the input offset voltage of an op-amp is usually defined as the differential voltage required to produce an output voltage of halfway between its two power rails. When the two rails are set to equal magnitude but opposite signs, as in a standard dual op-amp configuration, then this halfway point is ground. Moving the output voltage significantly away from ground usually changes the input offset voltage somewhat, and so it's important to keep it close to ground. Since OA2 is a large DC gain stage, the output from OA1 will have a voltage very close to OA2's non-inverting input, which, as you can see, is connected to ground. The input bias current and offset voltage of OA2 will affect it slightly, but it will be a very small effect and shouldn't affect the overall offset voltage measurement much. And thirdly, it buffers the OA1 output so that it has a very small load current, and its output is very close to ground. R2 is chosen to be relatively high, and a voltage close to ground through a high resistance to another voltage close to ground produces very little current. To limit the error due to the DUT's input bias currents, RFB and Rin need to be somewhat low resistance, which, without OA2, might load OA1 more than is desirable. In general, a loaded op-amp, especially one with a resistive load, will have a lower gain and may have altered offset characteristics, so you want to eliminate that effect so you can control it separately. If you want to measure the effect of load current on the input offset voltage, you can add a separate load on the output of OA1 to measure that dependency. We'll leave the analysis there, and I will take a deeper dive into all the sources of error in this circuit in a later video once we've introduced all of the op-amp non-idealities. Here are the values I'm using for the LM324 lab measurement. The gain is set to 121 using two 0.1% precision resistors for Rin and RFB. Errors in these resistances are one of the main sources of error for the measurement, and so the high precision resistors were necessary. The other resistances do not need to be precise, so I have used the standard 5% through-hole breadboard resistors. I set the gain to 121 rather than something larger like 1000, based partially on the resistances I had on hand, and because gaining up the offset to around 100 puts the offset at the high end of my DMM's millivolt range, so it works out well. In general, you should set the gain as high as you can to minimize your measurement error. This means a gain of 1000 for the millivolt V offset to about the 10 millivolt range, or higher gain for lower offset values. It also depends on what you're using to measure it. If you're using an ADC with a small maximum range, then you tailor the gain to the ADC's range rather than the op-amp's rails. The integrator is set up to have a high frequency gain of -1, with the corner frequency of its 0 at around 16 Hz, which will ensure a good phase margin for the outer feedback loop. We'll discuss phase margin in a later video. I expect the offset to be around 3 mV typical to 7 mV maximum per the LM324's datasheet, though it's important to note that the datasheet specifies an output voltage of 1.4 volts rather than halfway between the rails, and it measures it with a single 5-volt rail and ground rail instead. This is a little unusual for an op-amp, and I suspect it's because the part has an asymmetric output stage, which is generally not the case for modern op-amps. Today, I'm still going to measure the offset with plus and minus 12-volt rails, and at input and output around 0 volts. The offset will be a little different, but it's more instructive as this is the more common way of measuring input offset voltage for modern op-amps. Now let's move over to the lab. Similar to the other lab demos, we have plus and minus 12-volt regulators at the top of the breadboard. We measure the plus 12-volt rail to be approximately 11.78 volts. And we measure the negative 12-volt rail to be approximately negative 11.75 volts. So pretty close to a midpoint of ground. Now we look at the output voltage and see it is approximately 282 millivolts. Dividing this by negative 121, this translates to an input offset voltage of about negative 2.33 millivolts for OA1, which is a little lower than the 3 millivolt typical, but is well within expectations. Now let's heat up the chip a little to see how a slight increase in temperature changes the output. We see it increases after only a few seconds, and so probably only a few degrees Celsius. The output voltage increases by about 6 millivolts, which, after dividing by 121, our gain, is about 50 microvolts of offset change. This is important to note, as the temperature of a room tends to fluctuate, and so for non-temperature controlled systems, the input offset voltage will fluctuate. This is what is referred to as offset drift, and sometimes the datasheet of an op-amp will give a typical value for drift per degree Celsius, though it will rarely give a maximum value. So it's important to be cognizant of this effect when measuring offset, and not assuming the value at one temperature will be the same as the value measured at another temperature. The degree of offset drift also varies very widely from op-amp to op-amp, with lower offset op-amps tending to have a lower drift, and vice versa. Now that I've removed my finger, the DMM voltage is drifting downward with temperature reduction, so V offset drifts upward with temperature reduction. So that means that this particular op-amp's V offset has a negative temperature coefficient, but in general the sign of the temperature coefficient is random and not predictable without testing the specific op-amp chip. And finally we check the output voltage of the DUT to see if it's near ground, and it appears to be less than half a millivolt in magnitude, so very successfully very close to ground. That concludes this episode. In this episode, we introduced the non-ideal op-amp concept of input offset voltage, showed how it affects the non-inverting and inverting amplifier configurations, showed a good circuit for measuring input offset voltage, and demonstrated that circuit by measuring an LM324's input offset voltage in the lab. In the next episode, we will be introducing the non-ideal op-amp concepts of input bias current and input offset current. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. See you next time.